cellular, and then we have two hands-on sessions for the full concept that we were knowledge yesterday. And the talk today is going to be given by Claudio Mirasso on the topic of model and synchronization of neuronal movement. Thank you, Pera. Thank you very much. Thank you for inviting me to give a talk in the school. It's nice to have you here. I'm going to talk a little about the aspect of modeling and synchronization of neuronal systems. I guess many of you are not so familiarized with the topic, so I want to give a brief introduction about how can we model it, how do we model neurons and neuron population, which is interesting to work on. And then I will give you two examples that we have been working here. One is called the feature binding problem, which is a very well-known problem in neuroscience that I will discuss later. And the other one is related to aspect of synchronization that we call anticipated synchronization. I will finish with some summary and conclusions. So if you see, the brain is probably the most complex network that we know. It contains of the order of 10 to the 11 cells called the neurons, but also even more glia cells such as astrocytes. Each neuron is connected to about 10 to the 4 neuron networks, so we have a very large network. It is so large that in 1 millimeter, in cubic millimeter, we have the order of 10,000 neurons and 3 kilometers of cable of axons, dendrites. So it's really a very dense network. What do the neuron do? Well, neurons generate electrical signal. They have to communicate. They have to send signals from one to each other to others, and these signals are electrical. These signals propagate fast and over long distance, all along our body. These signals are electrical parts that are called action potential. So you will hear me say action potential many times. These are voltage spikes of the order of 100 millivolts that last of the order of 1 millisecond, and they travel along the axon. So as you see here, this is a cartoon here where you see that the electric pulse propagates and connect different neurons. It is important because these neurons find sequences of this action potential in various temporal patterns. That's the way the information is encoded. This is done in the presence of a stimuli such as light, sound, taste, smell, or touch. And here we have some typical responses of neurons, of certain neurons. These are experimental measurements. We see that there are very different patterns in all of these neurons. So neurons are very different. You have a large variety of neurons, and they respond very differently to different stimuli. In fact, if we see the neuron is quite simple. We have it's composed basically of 3 parts: the dendritic arbor, where the information comes from other neurons; the soma, which is the nucleus of the cell; and then the axon. And the axon can be myelinated or not. If it is myelinated, information travels faster, and that is important to send information, for instance, from the brain to our feet, because the distance is very large and the information has to be very quick. Other points that are of interest are the that are some parts in the myelinated axon, which makes the axon in contact with the extracellular media, and then I will show why this is important. At the end, we have the terminals. But this is a very sketch of the neuron, because neurons morphological much more complicated than this. And here we have 3 examples of very well-known neurons. These are pyramidal neurons of the cerebral cortex, but they are also in the hippocampus, many other regions in the brain. We have pyramidal neurons. Well, you see, this is the dendritic tree. Here the soma is in the middle, and we have an axon here. This is a Purkinje cell from the cerebellum. You see, it's completely different. It's a dendritic arbor is huge, but it has only 1 axon. And these neurons are almost disconnected among each other. So they really act as a single processor. Each of these neurons act really as a single processor due to this complex dendritic arbor. This one is an stellate cell, where axons and dendrites are mixed. You see, they are all together. You have the soma in the middle, and they have a stellar shape, where dendrites and axons are mixed. So these are only 3 examples, but there are many, many more. In fact, if we think what happens in the neuron, the best is to look what happens in the axon, because the axon is the part of the neuron which is more excitable. So if we can have a spike in the neuron, but if there is a spike, for sure it's in the axon. It might also be in the dendrite, but even if it is not in the dendrite, in the axon it is, because the excitability there is larger. So when we see the axon and we zoom in it, we can see that some spikes occur, and there are some parts in which there are no spikes. In this part, we can say that the membrane is more or less at rest. So the potential is more or less constant, which is not really true, but we can assume that the potential is at rest. And this potential is of the order of minus 70 millivolts, meaning that I have more negative charges inside the cell than outside, inside the axon than outside. And that is what happens. This is our outside part of the cell, the extracellular media, which is dominated by sodium ions, sodium plus ion, positive charges, and the internal part of the cell, which is dominated by potassium plus charges. Still, although these two ions are positive, there are negative charges that not only compensate them, but also make the internal part, the inside part of the cell, negative with respect to the external part. The neuronal firing, what we see here, is due to exchange of ions between the inside and outside of the membrane. So I will show you then a bit more in detail, but we have this channel here, ions enter and go out. Some ions enter, some others go out, and that gives rise to these spikes, neuronal spikes. The most important ions in general, and particularly in the brain, are sodium, potassium, and chloride. There are not many ions that participate. There are some others, but not that many. These ions that are important during the generation of a spike do also play an important role during the synapses when we couple two neurons. One of the first scientists that started to study this, the electrical properties of neurons, was Walter Nernst. He was a German chemistry, that computed or calculated the equilibrium potential differences between the internal and the external part of the cell. And he came up with a formula that, besides some constant, depends on the concentration of ions inside and outside of one ion, assuming that there is only one ion that is present, which is not true, because I told you that there are more than one. But still, this formula will be very important. So it depends on the logarithm of the ratio between the concentration outside with respect to inside, or the other way around. It doesn't matter. So what matters is the concentration of ions. And this gives you our equilibrium potential difference. Another important person is Louis Lapiquet, who is a French neuroscientist, who developed, let's say, the first model, or the simplest model that we know, to model the membrane of the cell. In particular, the membrane of the axon. As I say, that is the important part. So the axon it's like a tube. It has an internal part with some fluid, it has the membrane, and it has the external part. So the membrane can be modeled as a resistor in parallel to a capacitor, and same voltage, which is the resting potential that we know that exists. So this is a very, very simple circuit. If the resistance is constant, we know how to solve it from electricity. It's very simple to solve it. We apply a certain current from outside, the current flows, and then we can compute the voltage at any time. And what you see when you compute this for a certain input current, you have that the voltage starts to increase, but then it reaches a point in which I cannot describe anymore because the resistance is not constant anymore. The resistance starts to change, so I have to stop there. I cannot continue. So what I do is I do a reset of the variable. Since I cannot describe the dynamic of the neuron with this model beyond a certain threshold that I will discuss right now in more details, then I have to reset my variable to the resting state and start over. So I will have this kind of behavior for the membrane potential for a constant current. But probably the most important contribution to the study of the circuits came from Hodgkin and Huxley, two British biophysicists that were working in the middle of last century at the Plymouth Marine Lab. They were studying the giant nerve fiber in the squid. This is a fiber of the squid that is so big that they could put some electrodes there and measure how the current flow across the membrane. So they recorded the ionic current flowing through the membrane as its potential changes, because as I told you, below a certain threshold, the resistance is constant. Above a certain value, this resistance of the membrane becomes voltage dependence. So they use this measurement they did there and some and formulated a theory of the neuron firing. In fact, what they found is that changes in the membrane permeability allow charged iron to flow in and out of the nerve fiber, giving rise to the action potential. And this would be the resting state. If I put some current, positive current, I make positive current because I have to compensate for the internal negative charge. Then at some point I cross a threshold, a spike develops, it comes back and returns to the resting state. In this part, which is called the depolarization, what happens is that some ion channels open and sodium enters from outside. So since sodium is positive, it charges positively the internal part of the cell, the membrane potential rises, it arrives at the maximum where this channel closed, and potassium channel open. Potassium is inside, is positive, and goes out. So this is the repolarization part, which compensates the charge and leaves the cell again at the resting state. Between them is an interesting factor, which is the refractory period. This is a time of the order of 10 milliseconds for which the neuron is not able to respond to any input, which means that I cannot modulate neurons faster than 100 hertz, which might be more or less the maximum frequency at which neurons can operate. That is not really true. Some of them can have a much shorter refractory period, but in general, this is okay. This is right. Due to this study, Hoffman and Hasse, together with John Karin Eccles, won the Nobel Prize in Medicine or Physiology in 1963. If I want to model this and I want to do simulations, in particular if I want to explain some physiological effect that some experimentally can measure, I have to do the model. When I have to do the model, I have to decide, because I cannot model one neuron. I have to model population, and population might mean millions of neurons. So computationally, it is relevant. How do I do the model? Because if I have a very complicated model, the time would be too large. So one has to decide. And there are two options. One is the point neuron model, which is the simplest one that I'm going to explain right now. And the other one is called the multi-compartmental model. If I see my pyramidal neuron, and if I go back to the axon part, I can describe the dynamics of the whole neuron just by computing what happens in this point in space. So this is called a point neuron because it doesn't have a special distribution. I'm assuming that everything happens at the beginning of the axon, where not only the ionic currents are exchanged between the internal and the external part, as Kochinen has defined, but also synapses also or connection with other neurons occur in this point. So this is a very simplistic model, but it works quite well. If I want to do it more biologically or biologically realistic, then I have to start to put in parts which correspond mostly to the synaptic part, to the dendritic part. I mean, this would be the dendritic arbor, which now it is assumed that it is very important for neurons. We cannot model point neuron almost anymore because now we know that a lot of the computation is taking place in the dendritic part, so we need to incorporate that. And computers are being very fast now, so it is possible already to do more complicated model. Every this bar has to be described in terms of equations, so we have a lot of coupled equations here that I have to solve simultaneously, but that can be done already. And what I'm going to show you today, we will use the point neuron model. But which model to use? Because there are many models. So all of them are based in the very simple idea that the membrane has a resistance and a capacitance. For instance, this would be one function for where the sodium current and the potassium current and an extra current that can account for other ions that are less important but are there. Can be modeled. This is the capacitance, and then I have the external stimulus. So this is an electric circuit that I know how to solve. It's very simple. The equation for the circuit is that the capacitance times the derivative of the membrane potential is equal to the ionic current, which are this one, plus an external current that I can put from in the experiment, plus the synapses if they are connected with other neurons. But this is the equation I have to solve. If I manage to solve this equation, I can know the evolution of the membrane potential and all the currents. If you go to the website Model DB from Sensor Lab, they have 1,760 neuronal models. So you see the complexity is huge. But you can do something which is very general, and then you take a very general model and see what happens. Or if you want to reproduce some experimental result, then you have to take the model of the specific part, either the hippocampus or the cortex or the cerebellum. Whatever you are using, you have to use those models, because if not, the result will not reproduce experimental findings. Probably the most important one is the Hodgkin and Huxley model. The Hodgkin and Huxley model takes into account three equations. This is how they derive the model for the neuron. This is the left part of the equation, which is the membrane potential evolution in time. This is the external current that could include some synapses also. And these are the three currents that appeared before just as I, but these are more complicated, because this current has a term which is the maximum conductance here for that ion, and then it contains a parameter or a variable that describes the probability of that channel to be open. And this probability is voltage dependent. And it's not only in linear, it's at the power 4. This could be just as a simple analogy, as if we have 4 doors to open to enter the room. If the 4 doors are not open, you cannot enter. The same happens here. If the 4 doors for potassium are not open, potassium cannot flow from inside to outside. For sodium, there are 3 doors, and this I call a barrier. You can have 3 doors, the 3 open, but if I put a barrier, you cannot enter either. So these are activation gate. This is an activation gate. And this is the leakage current, which is an extra current that accounts for other ions that are not potassium or sodium, mostly chloride, which is also quite important. And this is the equation, which is a nonlinear equation, voltage dependent. This reversal potential here for sodium, potassium, and leakage are the nerve potential that I told you at the beginning. And this is the time evolution for these 3 variables, N, M, and H, which are just rate equation for the probability that the door, one of the doors that I told you, is open. This probability depends on the rate at which I open the channels times the probability that the channel is closed, minus the rate at which it closed, times the probability it is open. Very simple rate equation, but I have to solve the 4 of them together. Plus, these parameters that have been fit, but Hodgkin and Huxley to the experiment. These algebraic equations, so they are very simple. With this and the values you can have from the experiment, you can solve now the model. For instance, if I do that for a constant current, I get something like this. If I'm above threshold, this is the membrane potential. It increases and reaches the threshold. Sodium channels open, sodium goes in, the voltage grows, sodium channel closed, the potassium goes out, the pulse goes down, and then it repeats. And here we have the currents. The first one is the sodium one, and at some point here, potassium open and start to increase, and the leakage current is very small, almost no contribution. So this is what we suspected from the beginning, and this was proven by the Hodgkin and Huxley. However, the Hodgkin and Huxley model cannot explain many neurons, just the very little ones. In fact, Isikiewicz in a paper in 2004 discussed what are the possibilities of the different models that are. There are many models, I will not enter into details, but there are some that are very bad biologically plausible, so they are not very biological. And integrated and fire, I talk about Lapiquet, is one of that it is not biologically reasonable because it's only described the dynamic below threshold. So you cannot describe the evolution of the spike with that model. So it is not very biological. And on the other side, but computationally it's very efficient because it's a very simple model. But then you have the Hodgkin and Huxley model, which is very biological, but computationally is very hard. So if you have to model millions of neurons, the Hodgkin and Huxley is not the model to do that. In fact, 2 of the models that we used, and many people use, is the integrated and fire, that you see here is a first order differential equation that when I is constant, we can solve it analytically. In general, you cannot. And it has this reset term. When the voltage arrives to a certain threshold, something that I call the threshold, I have to reset the variable to a new value. Yes?
Where is the threshold?
The threshold is the point at which the channels, the sodium channels start to open. They are closed. You start to increase the threshold of the membrane potential voltage. At some point, these channels open. As soon as they open, there is where the threshold is defined. Is the time at which the neuron start to develop the spike. That is the threshold. You're welcome. The second model, which is very interesting because it's simple and very powerful, is the Izikevich model. This contains two equations. They are coupled. This is for the main brain potential, and this one accounts for some ions, mostly potassium, because the slowest one are the most relevant. It also contains a reset value, but not at the threshold, but at the value when the spike is at 30 millivolts. Then you do the reset of two variables. This model has 4 parameters, A, B, C, D. With that 4 parameters, you can generate almost any model of a spiking neuron. All these I'm showing here. This is atomic spiking. This is a phasic, means only one spike. This is atomic bursting, phasic bursting, and many of them, all of these can be generated with a Izikevich model by changing the 4 parameters. Besides that, I need to couple. That is only for the neurons. Then once I decided which model for the neurons I'm going to use, I have to couple them. And when couple them, I have to take into account that there are 2 kinds of synapses. One is electrical. The 2 neurons are in touch and some ions crosses the membrane between the 2 easily. That is a diffusive coupling that we know in physics. The second one, which is more important in the brain, is the chemical coupling. The chemical coupling involves the release of some substances from the presynaptic neuron, which are called neurotransmitters, that bind into the postsynaptic neuron, so the other neuron into the receptor. So it's a complicated chemical process. So you see here, I will not enter in detail, but here are release neurotransmitters that bind here and open channels. Which channels? Sodium and potassium and chloride. The same that we had for the axon. So the same ions participate here. The neurotransmitter, glutamate is the most important. The receptor are called AMPA and NMDA. They have different time scale, doesn't matter. What is important is that these are excitatory neurons. These promote the firing of the target neuron. So it tries the other neuron to spike. When I connect excitatory, I try the other neuron to spike. On the other hand, I have the inhibitory neurons. Neurotransmitters GABA, receptors GABA A and GABA B. Inhibitory neurons try to block the pulsation of the target neuron. One excites, the other blocks. By reducing the membrane potential. But again, I have the same ions participating. This excitation inhibition balance is very important. It occurs in the brain and is fundamental for its correct functioning. If I have an imbalance, this gives rise to disease such as epilepsy, schizophrenia, and many others. Most of these diseases that we heard a lot are due to an imbalance between excitation and inhibition. So this balance is really important. As I say, synapses, we have these neurotransmitters that are in the presynaptic part. If they act locally, that means over the receptor directly, glutamate and GABA, but there are others, neurotransmitters that have modulatory effect, which are more complicated. The receptor can be what is called ionotropic, which activate directly the channel, so as soon as they receive it, they open the channel. We talked about them already. And there are metallotropic, which are indirect activation. So I go to a place in the reception, and then this part opens the channel. So it's a 2-step process. In the simplest case, I extract the probability of the channel to be open as a rate equation again, which is the rate at which the channels are open times the probability that the channel is closed, minus the probability at which I close them, times the rate at which I close them, times the probability they are open. This IS, which is the opening rate, depends on the neurotransmitters, of the amount of neurotransmitters I have. If I don't have neurotransmitter, I cannot open the channel. And usually beta S is assumed to be constant. This is the simplest way you can model a synapses. The simplest. Then you can do much more. You can include plastics effect like short-term plasticity, long-term plasticity, homeostasis, different processes that change the strength of the synapses. We know that these are important for memory, formation, many things. But this complicates already the simple equation. I have to go further. Also, aspects of reinforcement learning can be used in learning process to model learning process. So I will give you now the first example. which is called the feature binding. And the idea is the following. When we watch something, for instance, I'm looking at the camera, you have to integrate all the information that you receive from the camera, the position in space, the color, the shape, everything. And that is processed in different parts of the brain. That means that you have to coordinate different areas of the brain to be activated at the same time to have a coherence perception of the object. And this is called, or was called by Singer in the 90s, the process called binding by synchrony. So separate movements respond to color, contents, textures, and so on. The synchrony hypothesis is that when the feature comes from the same object, and in this case the woman, these neurons fire at the same time in the same manner. Means I have to have a synchronization between areas that are far apart in space, but they have to exchange information because they have to synchronize. When the neurons fire at the same time and in the same manner, we perceive binding of the features that I'm observing. This was the problem. There was some experiment early at the end of the 90s of last year that showed that even in the presence of substantial coupling delays, different cortical areas exhibit isochronous synchronization at zero lag. Meaning that I have to couple different parts of our brain with distances that could cover of the order of 50 to 100 milliseconds, which is a lot, but they have to act simultaneously. And they found that experimentally. So the question was, how can two distant neuronal assemblies synchronize their firing at zero lag, even in the presence of a negligible delays in the transfer of information between them? How can we do that if we have to transmit information from one to the other? Well, we had some experimental evidence that, because for some years I have been working with my friend and colleague Ingo Fischer from IFISC as well, studying delay coupled semiconductor lasers. Semiconductor lasers are the lasers we have in the pointer, and they're very interesting because we see them operating in the continuous regime. But if I couple two of them, even a few centimeters far apart, the amplitude of the becomes chaotic. So it can start to fluctuate erratically. This was well known in lasers since many years already. In fact, we have experiment and numerical evidence that when you couple two lasers with a certain delay, this was of the order of 3 nanoseconds, which is about 30 centimeters far apart. Then you see that the intensity or the amplitude of the light in both lasers oscillates quite chaotically. It has some, it looks like being quite regular, but inside we have this chaotic dynamic. If you do the cross correlation between the two functions, what you see is that at zero, we hardly have any correlation, meaning that they are not oscillating at the same time. They are out of phase. And this maximum of the cross correlation occurs at the delay time. At the time it takes the light to go from one laser to the other, and this is quite symmetrical, because you can either shift one series for one side or the other, and you get the same correlation. So there is no correlation at zero time. So we cannot explain the feature binding assuming that we have only two oscillators that are separated one to the other. In fact, some months ago we said, what would happen if we add a third element? What would happen if I put an intermediate element? So I have the laser value 1 that couples to a second one, back and forth, but I have a splitter here which sends some light to a third element, which is here. So now I have 3 lasers coupled with delay. Same idea, but with a third laser. And what we found was very surprising for us. This is experimental results in the lab. This is the power of lasers 1 and 3. And this is the time evolution of the light in the nanosecond time scale. So these are gigahertz oscillation. And you see that they are very far apart to each other, more than 1 or 2 meters far to each other, but still the oscillations are completely in phase at zero lag. Well, if we look at the 1 and 2 or the 2 and 3, we don't see that. Actually, when we compute the cross correlation function, we have zero, the maximum of the cross correlation between 1 and 3, which are the outer lasers, and not between the outer and the middle. The two outers and the middle, the cross correlation has almost zero power at or zero coincidence at zero in both cases. So this is consistent with the case of two lasers, while this is new. And this is what we were looking for. Yes.
Saying that there comes still lag, but I can imagine that when you, let's say, have two lasers and then it's fixed on third laser, it takes some time.
Yes, it takes some time. There is a short transient, but it's quite fast, the process. And what is important that I didn't mention is that the central laser is not the leader in the dynamic. Because if you have the leader, then the central laser can force the other two to be in phase. But that is not the case. The central leader lags in the dynamics. So it's real emergent behavior of the complex system that occurs, that makes the outer laser to be in phase, certainly after quite a short transient. That is true. So how do we translate this to the neuronal system? Well, first of all, neurons are not lasers. Lasers are oscillators. Neurons are excitable systems, so they are not the same. They also couple not continuously. Lasers are continuously coupled. Neurons, no, they are pulse coupled. Every time you have a pulse, you couple. If not, you don't couple. So they are not exactly the same. So okay, let's try. So we took three populations, each of them composed by 4,000 integrated and fired neurons. 80% of these neurons were excitatory, 20% were inhibitory, which is the typical receipt for cortical areas. There was an internal random connectivity of 10%. This is also taken from the literature. This is the model I showed you before, the integrated and fired model. And this is the coupling, which contains a delay from D due to the separation between the two populations, or the three. And this is taken from a paper by Brunel in the year 2000. So when the populations are unconnected, you don't see much synchronization. You see quite a random pulsation. By the way, these are called raster plot. Every time one neuron spike, I put a dot. So this is the number of neurons, and this is the time, and a dot corresponds to the time at which that neuron spikes. So what did we do? Well, we took two populations of neurons. As I did before, we coupled them, we connected them excitatory because we know that long-range connections are mainly excitatory, and randomly with 0.25% of connectivity from neurons from one population to the other, and coupled with 15 milliseconds. Remember, but the time scale of the neuron is of the order of 1 millisecond, so 15 is a lot. It's much larger than the internal time scale of the neuron. So delays, it is important. So I have the two populations here, modeled by the integrated and fired system. And I put them to oscillate. And I see that after some time, I get population 1 and 2 completely out of phase, which means that when one is pulsating, the other one is not pulsating. Exactly what we saw in the laser case. So if you see here, we do the number of coincidences, which is equivalent to the cross correlation. We have 0 cross correlation at 0, and the peaks at the delay time between the two populations. So this is exactly what we saw for the laser, exactly the same. What happens if I include now a relay population? I have the three of them in a chain directionally, and then with 15 milliseconds from these two and 15 milliseconds from these two. So from here to here, I have 30 milliseconds. And if you see now, population 1 and 3 are completely in phase, are at zero lag synchronization. And this is also seen in this number of coincidence or cross correlation value. We have a peak here that shows that there is a maximum correlation of the two populations at zero lag, meaning that the two populations 1 and 3 are oscillating. Okay. Sí. Yes. Yes. They are lagging. No, they are in front of the dynamics. The intermediate neuron is lagging. If you take different time distances, then the maximum correlation occurs at the difference between the two delays. So it is still much smaller than the total delay. For instance, if I take 15, 16, the peak has appeared at 1, which is still much shorter than the 31 that will be the total delay. Yes. Yeah, well, depends on the coupling 1 to 3. I wanted to skip this part, but let me show you because we did some. some study in the thalamocortical circuit because everybody believes that the thalamus can be is like a relay element. So we start this circuit in which we have this will be the thalamus, which contains two populations, inhibitory and excitatory, and we have two cortical areas, and we put the cortical connection. And what if this connection is smaller or less stronger than these two, then it works perfectly. I will not enter in detail, but you see here how we have correlation at zero lag, and we don't have correlation between the thalamus and each cortical, but the two cortical areas are correlated at zero. And it seems that this thalamocortical circuit is responding to this zero lag synchronization that we found. So I wanted to talk to you about something different because I found this a very interesting problem, and this we study a lot with Raúl Toral, which you probably know also. And the idea is very simple. If I have two coupled systems, X and Y ruled by the same function, Fx and Fy, and I couple them from one to this one with a diffusive coupling, then X of t equal Y of t is a potential solution. And this is a fixed point, and this solution might be stable for large enough K. So if the coupling is large enough, this solution is stable. This is clear, we all know this is very simple. But what happens if I have a delay in the second population like here? So this is my equation now, but now the coupling is not instantaneous, but it contains a delay variable in the receiver side. So now the solution of the equation is not y equal to x, but it's y equal to x t plus tau, which means that the receiver is predicting what the sender is going to do in the future, in the time t plus tau, at the time t. So this is a solution of the equations, and it has been proven that can be structurally stable. This was proposed by Henning Boss in 2000. So this is the idea. In the delay synchronization, this switches on, then this one, but if I'm in the anticipated synchronization regime, it is the other way around. So it looks very anti-intuitive, but it has the explanation. We did a lot of studies in different systems, mostly in oscillators, in excitable systems, but all from the modeling point of view. And at some point, we found this paper by the group of Bressler in the United States that we published a PNAS paper in 2004 and a science paper in 2012, measurements in monkeys, measuring different areas of the monkey while doing a certain task. One is a memory task, the other one is a trial task, a go-no-go task. And they measure the coherence between the activity of the different populations that they were recording and the grain-share causality, meaning how the information flows, from where to where the information flows. With the coherence, you can also compute at what time the population activates. So I can know, if I compute the coherence between 2 and 1, I can know when activates 1 and when activates 2 and 1. That you can do. And interestingly, they say in the paper, without any explanation, that causality relations were generally inconsistent with time delay values. The sign of the time delay did not predict the direction of causality. And they concluded that the relative phase between the two populations is not a reliable index of neural influence. This is exactly what we wanted to find. That you have two populations that are coupled in one direction, but the receiver is activated before the other one. And that is what you compute with the sign of the delay. The delay is negative because the receiver population activates before the sender one. But if you compute the grain-share causality, we measure the directionality of the flow, gives you in the correct way. So we do this, let's go to a population model. As before, we have a master population, excitatory and inhibitory neurons, we have an inhibitory population, and we needed a negative feedback. A negative feedback can be done by an inhibitory neuron, because inhibitory neurons has negative feedback. And that is what we included. As a negative feedback, we included a population of negative neurons, of inhibitory neurons here. We use the security model that I talked before. We included neuronal diversity. Each neuron was receiving an independent Poisson input, so we make it complicated, not that easy to reproduce. We included chemical synapses, short-range interactions here were excitatory and inhibitory, long-range interaction here were excitatory. while here we're inhibitory. And this is what we found. If we compute the membrane potential, which is the average, more or less, of the membrane potential of the whole population, this is what you see. If you have the delay synchronization, this is the master population in black, and this is the slave or the receiver population in red. So you see that the red one activates after. That is what you expect. If you send information from A to B, you expect B to activate after A. But if you change some parameter that I will show you now, you see that now the receiver population pulses before, although at the beginning was delayed, but some point evolved faster and pulses before the master one. So you see that we have anticipated synchronization. The receiver is pulsing before. In fact, if you change the inhibitory conductance, the important parameter is this one, is the inhibitory conductance from this population to this one. You can go from delay synchronization to a region of anticipated synchronization and going back to a delay synchronization. So by changing this parameter that can be controlled, you can move from one to the other. In fact, if you change the excitatory connection, you can have another scenario, but again, we have a region of anticipating and a region of delay. So Bressler gave us the data they have for the monkey. We reanalyzed the data they had, and we found cases in which grain cell causality and phase difference have different direction, which we call anticipated synchronization. Grain cell causality and phase difference have the same direction, which we call delay synchronization, and some regions in the bidirectionality, but stronger in one. So this is plotted here. But this one interesting point, which is this one. I go from region 2 to region 1, which is red, means that 1 activates before 2, but the grain cell causality is positive. Now we realize that we didn't need 3 population because we have already inhibitory neurons in the receiver population, and we can play with the value of the inhibition here. This is what it is got from the experiment. The data, this is the local field potential, the average membrane potential of the population. This is the coherence function with a peak at the oscillation frequency, and this is the grain cell causality, which indicates that goes to 2 to 1 is large and from 1 to 2 is small, meaning that the information really goes from 2 to 1. But the delay in the activation time is minus 8 milliseconds, indicating that the population activates 8.7 milliseconds after this one. And this is what we get from our model. We constructed this to give exactly this positive grain cell causality, which is, this is the coherence, which matches the experiment. This is the grain cell causality, which is positive from master to slave, as we constructed. And we obtain a delay time of minus 8.2 milliseconds, which explain why they observed this difference in the experiment. So I will finish. If you have any question, I can give it to you, but let me go to the... I don't want to tell you more to the conclusions. I told you about 2 kind of simulation that we did. We have proposed a mechanism that gives rise to 0 or almost 0 lag or phase synchronization in long-range synchronization in neuronal populations. Every low element must mediate the dynamic, and it is possible that the thalamus act as this relay element, although there are other options like the hippocampus. There are other populations that can play that role. In the second part, I show that anticipation synchronization can occur in excitatory and inhibitory neuronal circuits. The strength of inhibition regulates the transition between delay to anticipated synchronization. There are experimental observations that were reproduced by our model. In particular, I show you what happened in the monkey's cortex, where negative activation time with positive grain cell causality was observed. And I didn't show you, but I have the results, that in the visual cortex, it has been observed shorter time lag between the retina to the thalamus than if it goes to a relay element, meaning that the directional information transmission takes longer than going through a relay element, as expected. So that is all, and thank you very much for your attention. Thank you for all your questions.
Like the phase format, it's like sort of a phase format that you can have many relay elements that can like introduce the phase format with a different frames, and therefore it is problematic to build causal association based on let's say how manipulate program itself, but this doesn't tell you anything about the underlying.
You are completely right. You are completely right. But that is not what the physiologists know. They follow their intuition and they say, if this activates first, this has, if that, I connect this to this has to activate first and this then. And they measure the phase, and most of the people measure the phase and they are happy with that. But the result might be wrong. That's why the phase might not be the correct description for the activation time.
And if you if you have certain probability, is it like it's somehow it's better correlation, right?
What?
In the science.
Gives you information flow. For that. Yeah.
And isn't this same problem in different like you measure like some type of directional current, and what I'm trying to say is greater causal probability, but good way of measure.
Well, I mean, there are other options, but most people in neuroscience use differential causality. In general, the results look okay, but you might have some troubles, in particular if other areas are participating and you cannot account for them, because when you measure, you cannot measure everything. You have 2 areas, but you have many others participating, and that could cause a lot of problems. But in general, as an indicator, I would say that is reasonable, at least. Maybe not perfect, for sure not perfect, but at least reasonable. Thank you.
Behind it. So what about the gradient phosphorus or some other?
You can compute it, but you will get the same, basically. Yeah. I mean, it is possible. We have in other words, we have other indicators than nonlinear indicators for interactions. We published a paper some years ago in which we computed different indicators over the same experiment, and the correlation was almost identical to all others. You have to have a very strong nonlinearity, which is not always the case in the brain, to have differences between the indicators. But usually, correlation and very simple indicators are enough to measure brain activity. Yeah, for sure, people that are in physiology, they are not that expertise in mathematics, so they tend to use simpler indicator, but when you try with more difficult one, you don't gain much most of the time. Yes.
Areas what stops that signal from leaking out into other areas of the brain? Why are there only these localized areas before?
Well, it's only because they are connected.
Are they disconnected from the areas?
No, they disconnect when they stop the activity. When they change the activity, they somehow disconnect. You measure.
They are connected to other regions.
Yes, to other regions, they are.
What stops the signal from entering those other regions?
Nothing.
So they do. So if you have 2 parts synchronized signaling, these signals are also going around to other parts of the brain.
In the brain, you cannot do much because everything is very connected. But and then the problem, that's a problem when you do measurement or experiment, because you are recording a very small parts and you have a lot of other areas that are participating, and you are never sure how the connectivity is, if you have influence from other areas or not. You have to assume that they are, but at the end you have to say something. And that is what you can do. You cannot do more. For the moment, this has not been tested experimentally, although Wolsinger, who is the expert in the feature binding, was very happy with our explanation, and he thinks that this is the explanation for the feature binding, the relay through a third area that could be the thalamus or other one, and many other areas can participate, but this would be the basic mechanism behind the synchronization, which probably is more complicated than this one. These are very simple models as well.
So of course,
Thank you. Thank you very much.
Raúl me ha enviado un email, pero no está el email de ejemplo que tú mandas. Si no puedes reenviar. Me pido a Raúl que me lo reenvíe, pero no me lo has enviado, así que. Antes sí, no.
Sí, seguro.
Muy bien,
Gracias. Me alegro.
que preparar.
Sí, claro.
Que no me ha dado tiempo a muchas lógicas abiertas antes de levantarme. ¿Qué tipo de inspiración, por ejemplo, a la hora de hacer redes sociales, en el sentido de aprendizaje o lo que sea, se puede aprender de esto?